In this video, we're going to look at radix sort. Now, radix sort will put elements into a lexicographic order. So where bucket sort would sort n elements based on a single key, radix sort will sort n elements where each key has d keys. So how do we sort elements by multiple keys? We need to specify which keys are more important. So we have to have an ordered two keys. So if we have d keys, an ordered list of them is called a d tuple. So we say that key I is the ith dimension of the tuple. So we have the first and the second, the third dimension, and so forth. You've seen this before with Cartesian points in two-dimensional, three-dimensional space. So this would be a two tuple or three tuple. But the order of keys matters. So for example, if we had in two-dimensional space the point 0, 1, then we have x is 0, y is 1. This is our 0, 1 point. This would be different than the point 1, 0. So with a tuple, the order matters here. And just like with our keys for elements, we want to sort them based on a specific key. Now, what is a lexicographic order? So we could define this recursively as kind of comparing two d tuples based on here we have d keys and here we have d keys. So we say that this element is less than the right one if their first dimension, if the first one is smaller than the second one when it comes to their first keys, so x1 is less than y1, or if those two values are the same, then we'll check to see the remaining keys. So the result of this is that we compare by the first dimension, then we compare by the second one if they're the same, and then if those are the same, we compare that by the third one, and so forth. So this is really kind of like the most significant dimension, and then the least, down to the least significant dimension. So a lexicographic sort we can accomplish just by repeatedly using any stable sorting algorithm on each of the d keys from least to most significant dimension. So this is from the least significant dimension all the way down to the most significant dimension. So the order that we obtain as a result will be that items are ordered by their most significant dimension, since that was the last sort that we did. And when their most significant dimension has the same value, then they're next ordered by their second most significant dimension, since that was the second to last sort we did, and we used a stable sort which preserved the order of elements from the previous step. So for example, if we wanted a record of people where they're all ordered by their last name, so we've got all the, I don't know, the Smiths, all of those people come after the Guarneras, and maybe we have a few of them. We have Drew Guarnera and Heather Guarnera and John Smith and Jane Smith and so forth. If we wanted an order of people so that they were first ordered by their last name, and then for people that had the same last name, then for them we ordered them by first name, to accomplish that lexicographic order, we can use this very simple, just repeatedly calling stable sort by first calling stable sort on first names, and then lastly calling a stable sort on last names. And why we do it in that order is because stable sort will keep the same ordering of elements. So the next time we call, the last time we call stable sort by last name, then our resulting order will be based on last name, and then for those people that had the same last name, since we used a stable sort, their original order will be preserved. Now the runtime of this is just based on the runtime of whatever stable sorting algorithm we use, and we call it d times. So our total running time is big O of d times however much it costs to call that specific stable sorting algorithm. We've talked about a few of them so far. So for example, if this was our unordered sequence that we wanted to sort, and we have a three tuple here, and this is our most significant dimension, and this is our least significant dimension, our lexicographic sort will first sort on this least significant dimension in ascending order, and then using this as the input, perform another stable sort using the second dimension. Now for those elements that had the same value, say here and here, they have the same key, but why this one comes before the next one is because their second key is because of their second key. So we had this item came before this one in the previous order. Here's the first one, and here's the second one, and we kept them in that order when we did stable sort again. And then we take this as our input and use that to run stable sort on the third time now on the most significant key. And this is basically what radix sort does. Remember that bucket sort is a stable sort. Bucket sort works on, we have n elements, one key to work with. That key is in the range of 0 to r minus 1. Radix sort works by calling bucket sort d times, once for each dimension, first on the least significant dimension and then lastly on the most significant dimension, which means that our running time is however many, big O of however many dimensions we have, times the cost of how many times we call bucket, times the cost of bucket sort, which is n plus r. So in this case, radix sort will call our bucket sort d times, and we also have that each of the keys that we're sorting by, all of our keys, so for each of the n elements we have d keys, and all of those keys are within the range of 0 to r. Okay, so this is a pretty straightforward application of bucket sort, but what's interesting is how we can use radix sort even when the keys that we're sorting by aren't tuples. So instead, if we have n elements, each of which have only one key to sort by, we can actually transform each key into multiple keys and then use radix sort. So for example, say we wanted to sort a list of binary numbers. We can transform each key into b integers, since our binary number has b bits associated with it. Now each element that we have is a b tuple, where the keys are integers in the range 0 to 1 because they're bits. Then we can apply radix sort, where the range of our keys is, here r is equal to 2. So we're going to call bucket sort b times, so this is our radix sort, right? We're repeatedly calling bucket sort essentially, but we're taking the elements which have only one key, which is that entire binary number, and we're transforming it into b keys. So essentially making it one key for each bit in that binary number. From here we have the least significant bit to the most significant bit. So in this case, our sorting algorithm runs in big O of b times n time. Why? This is because we have, here we have big O of however many dimensions we have, which is b, times the cost of bucket sort. Remember, bucket sort runs in little n plus r time, where r is the range of keys. But in this case, we know the range of our keys because they're bits. So this is big O of b times n plus 2. When we put this properly in big O notation, we get rid of these constant coefficients in lower order terms, and this is big O of b times n, where b is the number of bits that we have, n is just the number of elements we have. So if we have, let's say we know we have 32-bit integers, 32 is a constant number, we can sort those in linear time. So if b is a constant number, then we have a linear time sorting algorithm. So for example, let's say here are the 5 binary numbers that we want to sort. Using radix sort, we'll transform each of these single keys into, instead, since these are 4-bit integers, we'll now have 4 keys from our, here's our most significant bit to our least significant bit. And we want to sort them. So to do that, we're going to first sort based on the least significant key, then the second least significant key, so increasing significance of our bits here. Now the next time we'll sort based on the second bit, and then our last sort will be based on this first bit. So this is our resulting sorted sequence of an ascending order of those binary numbers. So we ended up doing bucket sort 1, 2, 3, 4 times, but the idea here is that we have, for example, A and C. We have that they have the same most significant bit. They both have a 1 there, but the reason why A comes before C is based on this next most significant bit. And why A comes before C is because in the last stable sort that we did here, we found that, oh, A has a 0 in that second bit position, and C has a 1 in that second bit position, and so we preserved this order. When we ran that bucket sort our last time, since they have the same first bit here, then we kept the same order that what they had in the previous time that we ordered them. So this is the power behind radix sort, using bucket sort as a stable sort, and then showing how we can take some element which has only one key and break it up into multiple keys so that we can call bucket sort on each of those keys. Okay, I want to show one other example here, which is using radix sort in order to sort integers in the range of 0 to some polynomial with respect to n. So this is n to some power c, where c is a constant number. Maybe this is 3 or 4 or 5 or something, but we have some constant here. Now, how could we do this? Say, if we didn't transform our key at all, we just have each of the n elements we have has one key, and that key could be as large as n to the power of c. If we were to just use bucket sort, just called bucket sort once without breaking up our key into multiple keys, we know that the cost of bucket sort is big O of n, how many elements we have, plus the range of those keys. But in this case, the largest key we could have is a polynomial. This is n to the power of c. So that means if we tried to use that here, we would get a polynomial time sorting algorithm, which really isn't good because we know we could at least sort in n log n time using one of the other sorting algorithms we talked about, like heap sort or merge sort or something. So this wouldn't be a good approach. Instead, we can try and break up our key into smaller keys, multiple smaller keys. So we could try and use the same approach we did last time. Maybe we just turn this into a binary number. So let's try kind of our first attempt here. We'll represent each key as a binary number. Whoops. So this means we put it in base 2. So we have a few bits, but each bit goes from 0 to 1. So we have our runtime is big O of however many dimensions we have times the cost of bucket sort. So bucket sort is little n plus r, but in this case, if we're representing it in base 2, then all of our keys are either 0 or 1. So we would have here 2. We've got 2 options. So now the cost of this just depends on how many dimensions we have. If we represent our key in base 2, and our key could be as large as n to the power of c, how could we represent n to the power of c in base 2? So the number of dimensions we would need is, if this is, we're putting it in base 2, this is log base 2 of that largest number we'd have is n to the c power. Now, we could take this power and just use those rules of logarithms. We know this is equal to c times log base 2 of n. But this still isn't good, because if we plug this in now, we've got d, which is some constant, times log base 2 of n, times n. This means that we end up getting something which is n log n. which this isn't any better than what we had before. Again, just using heap sort or merge sort. Okay, so we can try and represent this in a different way now. Base 2, maybe this is too small. We'll try something a little bit larger. Let's say now we represent each key. Let's go put this in decimal format. Maybe we could use hexadecimal or something else, but let's start by putting it in decimal format, in base 10. The standard number system that you know and love. So now our runtime, this will again be based on how many dimensions we have, but our keys are in a different range now. Our running time will be however many dimensions we have times how many elements we have, which is n, plus the range of those elements. Now if we put it in base 10, our keys, they won't be bits anymore, but since they'll be in base 10, they'll be digits, so it'll be anywhere between 0 and 9. So we have here 10. But again, what's d? How many dimensions? If we have to represent some number in base 10, the largest number we have is n to the power of c. So how many dimensions, how many times we'll ultimately have to call bucket sort is log base 10 of n to the power of c, which is still some constant number times log base 10 of n. Now when we put this in big O notation, it really doesn't matter which log base we use, because we can go between different bases of log n and only change by a constant amount. So you'll notice I didn't even put log base 2 here. So we still end up getting something which is unfortunately n log n. Still not very good. But we can do better. Instead of using base 2 or base 10 or base 16 or base 500, what we want to do is get rid of this logarithmic part of how many dimensions we have. We don't want it to be dependent on n. So instead, this is our last attempt here, we'll represent each key in base n. Right? So this means that the range of our keys, they won't be bits or digits, they'll be integers, but they'll each be in the range of 0 to n minus 1. Which means our running time now will be big O of how many dimensions we've got times the cost of bucket sort, which will be n plus the range of our keys. Now if we're putting it in base n, each of those smaller keys will be between 0 and n minus 1. And the number of dimensions that we have will be, if we put it in base n, now we have log base n of n to the power of c, which now we've got, this is c times log base n of n. But this is where it gets cool, because this second part, they cancel each other out. Log base n of n is 1. So we're just left here with c. So if we put our key in base n, if the largest key that we could have is n to the power of c, then the most number of dimensions we'll need to represent it that way is c, which is a constant number. So that means our running time now is big O of some constant number times n plus n, which is 2n. So we just have some larger constant number times n. We finally have a linear time algorithm. So even for very large values of r, we can still sort those elements in linear time. So this is what the next explanation here is. We can represent each of those integers as a c tuple. So this is how we would represent it. So rather than a bit string or in decimal format, this is in base n. So we have, this is our least significant, not a digit, not a bit, but least significant key, next to least significant key, and this is our most significant key. Right? Then we can apply radix sort, where the range is n, each of these keys here is somewhere between 0 and n minus 1. And then radix sort works by calling bucket sort for each key. So first we'll call bucket sort to sort by our least significant key, and then kind of increase based on these key values. Our last bucket sort will be called on our most significant key. So our total running time is big O of c times n, where c is a constant. This is just based on the power, n to some power of this is our largest value, our largest integer that we're sorting by. Okay, now the last thing I want to mention now is, since you've seen a bunch of sorting algorithms, you can finally understand and appreciate this comic strip from XKCD, which gives a list of a few joke sorting algorithms. So this is a joke. Please don't take these and memorize them and put them on an exam or something. But these are just kind of funny, I think, and you can appreciate them now. So we have a half-hearted merge sort, which is kind of like the merge sort that you've seen, except it's not fully implemented. It'll at least break a list up into the first half and second half, but then it never actually merges them, it just puts them right after the other. Then we have the fast BOGO sort. We actually didn't talk about BOGO sort in this class because it's the most inefficient sorting algorithm that there is. It's not even guaranteed to finish because the way BOGO sort works is just by repeatedly shuffling an input sequence and checking to see if it's been sorted yet, if it just happens to have been put in the correct total order. And then if it hasn't, it just keeps shuffling it until it has been sorted. But this is a fast implementation of BOGO sort by only shuffling a list log n times. And then there's the job interview quicksort, which tries to do quicksort by correctly picking a pivot, and then it tries to divide the list in half, but then it pretty quickly gets kind of carried away from there, forgetting how to use the pivot to break up a list and then how to put it back together again. So it gets a little crazy. But my personal favorite is the panic sort, which will check to see if a list is sorted. And if it is, it'll return it, so that's good. And then 10,000 times it will pick a random pivot and then use it to break up the list based on that pivot, and then put the list exactly back together the way that it was before, and then check to see if it's magically been sorted yet. And then maybe just a few extra times check to see if it's sorted, and then if it hasn't magically been sorted by then, it'll just set the list to be empty and recursively delete every file on the computer, and then shut down the computer and return a sorted list at the end of it anyway. So that's my personal favorite. But again, these are joke sorts, so don't use them on an exam. This is just from XKCD. All right, if you have any questions, please post on Piazza, reach out and let me know.